I'm releasing a token for EatTheBlocks and I will distribute a part of it for free with an airdrop. In this video, we will build the airdrop system for the token of EatTheBlocks. An airdrop is just a bunch of token transfers on the blockchain. It looks simple, but there are a couple of caveats like how to minimize gas spending and how to keep it decentralized. If you don't know me, I'm Julien, and on EatTheBlocks I teach blockchain development. Before you work on a solution, you need to first understand which problem you are trying to solve. So let's go over the rules of the airdrop. The total supply of the EatTheBlocks token is 1 million. Out of this 1 million, 10% will be distributed for free for the airdrop. Half of the airdrop is the basic allocation. This will be shared among all the people who register for the airdrop. The other half is the bonus allocation. It will be shared among the first 1,000 students of the courses of EatTheBlocks. For example, if we have 11,000 people who registered for the airdrop, including 1,000 students of EatTheBlocks, 10,000 people will each receive roughly 4.5 token, which is 50,000 token divided by 11,000 addresses, and 1,000 people will each receive roughly 54.4 tokens, which is 50,000 token divided by 11,000, plus the bonus allocation, which is 50,000 divided by 1,000. Alright, so now that we understand the problem, let's work on a solution. My first attempt for the airdrop is to use a centralized distribution. First, recipients register for the airdrop. The backend records the addresses and store them in a database. At the end of the airdrop, the backend will calculate the allocation of each address and send a giant transaction to the airdrop smart contract with a big list of all addresses and their allocation. The big advantage is that it's very simple. Another big advantage is that recipients don't have to pay any gas fees. They just register with their address and they magically receive the tokens later. However, for me, the creator of the airdrop, this will be quite costly because the big transaction that will be sent to the smart contract to distribute the tokens will consume a lot of gas. On top of it, this transaction probably will not even fit in a single block because of the block gas limit that imposes a limit on the sum of all gas spent by all transactions in a block. This means I will need to send several transactions to complete the airdrop. Another issue is that it's easy for anybody to register many addresses and get a larger share of tokens. And this is also very centralized because the process relies on a backend to do the airdrop. If you want to just keep it simple and don't mind the cost, you can use this method, but I felt like we could find a better solution. Instead of having people registering to a backend, they could directly register on the smart contract of the airdrop. At the end of the registration period, me or anybody else could execute a function of the smart contract to distribute the tokens. The code of the smart contract will calculate the amount of tokens to be sent to each address based on the number of addresses who registered. In terms of gas cost, me or the person who sent the transaction to trigger the token distribution would pay a very high gas fee because the airdrop smart contract would have to loop through all the registered addresses and distribute tokens to each of them. And like for the previous solution, would probably hit the block gas limit, which means this token distribution would have to be done in several batches. It would really make the code more complex. On top of it, it wouldn't work for the bonus allocation since we need to flag the addresses of EatTheBlocks students to give them their bonus. So we're not going to use this solution, we need to try something else. Merkle trees are data structures that are used in a lot of blockchain core protocols. They're allowed to verify that a transaction is included in a block or not, with very little data required. They can also be used in our airdrop to verify that an address is part of a list of whitelisted addresses. It would work like this. First, recipients register their address for the airdrop. The backend store addresses in a database and flag the addresses that belong to an EatTheBlocks student to give them a bonus allocation. Then, at the end of the registration period, the backend calculates the allocation for each address based on the total number of addresses registered and on the student flag associated to some addresses. Then we are going to build two groups of addresses, the basic allocation and the bonus allocation. For each group, we are going to calculate the Merkle root and the first row of the Merkle tree. The Merkle root is obtained by recursively hashing all the addresses. And the first row of the Merkle tree is obtained by individually hashing all addresses. Then we store the Merkle root in the airdrop smart contract and we publish the first row of the Merkle tree. After, each recipient can individually claim their tokens by sending a transaction that contains a Merkle proof. A Merkle proof is a series of intermediary hashes that can be used to prove the inclusion of some data in the Merkle tree. The Merkle proof can be built independently by each recipient since they have access to the first row of the Merkle tree. The Airdrop smart contract can then verify the inclusion of the address in the group of whitelisted addresses by using the Merkle root that was stored before and the Merkle proof provided by the recipient. I really like this solution because it's elegant and it uses intelligently some crypto primitives to minimize gas spending. I even found some repos on GitHub that help you to calculate and verify a Merkle proof, but I didn't understand the code well enough to really feel confident with the solution. I'm a practical guy and I don't want to just use the most sophisticated solution just for the sake of using some fancy code, so I decided not to use this solution and to keep searching for something more simple. After having studied all these solutions, I finally found something that we can use for our airdrop: signatures. For the first step, the recipient will register his address. Then, at the end of the registration period, the backend will calculate the allocation of each address. Then, each recipient can claim his token by first asking a signature from the backend and then sending a transaction to the airdrop smart contract containing the signature of the backend. Before the backend produces a signature, it will check that the address was registered before. The signature will be done by using the private key of the admin. The data being signed is the address and the allocation of the recipient. The airdrop contract will check that the signature is valid and signed by the admin. If the recipient tries to claim token for another address or for another amount than the one that was signed, the signature will be invalid and the whole transaction will fail. After, once the airdrop contract has determined that the signature is valid, it will finally send the tokens to the recipient, and that's the end of the process. Okay, so next we are going to code the airdrop smart contract. Let's have a look at the code of smart contract of the airdrop. So this is the GitHub repo of the token where there is the airdrop. So this is a standard truffle project. And the smart contract of the airdrop is inside the contracts folder. So this is airdrop.sol. So let's see this. So we're importing the ERC interface of OpenZeppelin because we're going to interact with the ETB token. We define our smart contract, we define an address for an admin, so this is going to be used to verify signatures. Then we define a mapping of addresses to Boolean value. This is to prevent people from claiming the airdrop more than once. Then we have a pointer to the token of EatTheBlocks, then the total amount that we've already distributed in the airdrop, and maximum amount for the airdrop, which is 100,000 token, which is 10% of the total supply. Then we define an event for every time we process an airdrop with the recipient of the airdrop, the amount, and the date. Then in a constructor, we specify the address of the EatTheBlocks token. Initialize the admin variable, that's the address that deploy the airdrop contract. We initialize a pointer to the EatTheBlocks token, then a function to update the address of the admin for more flexibility. And after, the most important function, claim tokens. That's the function that each recipient will have to call in order to claim their token. So you specify the recipient of the token and the amount, as well as the signature provided by the backend. Then we are going to compute the message that was signed in the signature provided. So for that, first we concatenate the recipient and the amount with abi.encodePact. Then we pass this to the hashing function of Solidity Ketchak256. Then we're going to hash this again with the prefix function. So we scroll down, this is defined here. So we're going to hash our first hash here a second time, and we're going to prefix it with Ethereum sign message. So that's a standard prefix that is added in a sign-in function of Ethereum. So that we have a hash of a hash here for the message. And after a very critical part of the process, we are going to make sure that the signature is valid. So for that, we're going to call the recover signer function. We pass it the message we created and the signature that we got as argument. and this is going to give us the address that created this signature for this message, and we want this address to be the admin. And if either the message or the signature are wrong, recover signer is going to return the null address, which will be different from the admin. So this require statement will fail and the whole transaction will stop here. So then let's see how recover signer works. So we pass it the message we created as well as a signature that was created by the backend. Then we're going to pass the signature to split signature to extract VRS. So these are the 3 elements of signatures on Ethereum. So this function split signature is defined just below. And here we are going to use assembly to extract R, S, and V. So this is quite low level. R is what we have for the 32 first byte. Then for S, this is the next 32 byte. And finally, V also the next 32 byte. Finally, we return VRS. So we don't need to understand exactly what are these elements, but all that matters is that we need this revalue in order to call EC recover, which is a built-in function provided by Solidity that allows to verify a signature and tell us which address signed a message. So first we pass the message and then the 3 elements of the signature, and then we go back in claim token. So hopefully recover signer is going to return the address of the admin. So we pass this require statement. Then we check in the mapping process airdrops that this recipient didn't claim his airdrop before. Then we also make sure that we haven't reached the maximum airdrop amount. So normally it will not happen unless the backend does a problem in the allocation and over allocate the airdrop. This is a safety check here. Then we update the process airdrops mapping so that the recipient cannot claim its airdrop a second time. Then we increment current airdrop amount with the amount that will be allocated. Then we do the actual airdrop here, so token.transfer, and then we emit an event. So this can be useful for frontends that want to monitor the evolution of the airdrop. Okay, so that's it for the airdrop contract. So next I'm going to show you the test. So we're going to test folder airdrop.js. All right. So first we import a helper expect revert. This is to do some assertion for unhappy paths, basically when a transaction fails. Then we import contract artifact for the EatTheBlocks token and the airdrop. So these are objects of the Truffle framework that we can use to interact with the smart contract. Then we define a contract block. So in Truffle, you always have to put your test in a contract block. So we define the name of this block. Then we receive an array of addresses that are provided by Truffle, and we extract the first one, that's going to be the admin. Then we define a couple of variables, a pointer to a deploy instance of the token, same for airdrop, then the total supply of the token, then the total value for the airdrop. And so before each test, we are going to run this code. So we deploy a new EatTheBlocks token, we deploy a new airdrop, and we pass it the address of the token. We also transfer some tokens to the airdrop smart contract so that it can distribute these tokens. Then I created a utility function here, create signature. So we need the code inside in several tests. So that's why I extracted the common path in a function here. First, we create a hash of the message that we want to sign. This is a hash of the recipient and the amount of the airdrop. Then here, this is the private key of the admin. So I'll look at the code of Truffle on GitHub in order to find this private key. Then we use the sign function of Web3 to produce our signature. So we pass it our message and the private key of the admin. So here basically we simulate the backend. It's as if our admin authorized this airdrop and we extract the signature. So here, very important detail, Web3 has actually several signing functions. Some of these functions require you to have an access to an Ethereum node, but in our case, we just wanted to produce the signature based on the private key that you provide in input. So it's very important that you use this exact signing function, otherwise you're not going to have the same result. Then we return the signature as well as the recipient and the amount. And after, we're gonna write our actual test. So the first one, the most simple, this is the happy path when everything goes well. So first we create our signature. Then we're gonna call the claim tokens function on the airdrop. We pass it a different argument, recipient, amount, and signature. And hopefully it goes well. And after, we're gonna check that we actually receive the token. So we get the balance of the recipient, and here we're going to assert that this balance is correct. Then we're going to test the unhappy path. So that's very, very important. In general, most of your tests will be tests of the unhappy path. You shouldn't just test the happy path. So in this test, we're going to make sure that we cannot claim an airdrop twice for the same address. So we create a signature, we claim the token once, and after we try to claim the token a second time, and we are expecting a required statement to fail with the error message airdrop already processed. And here we have this elegant way to test for failing transaction with the expect revert function of OpenZeppelin. Then another unhappy path, we're going to test that we cannot airdrop above the airdrop limit. So first we're going to create a signature for an amount that is too big for the airdrop, so 100,001 token, and then we try to claim the token for this, but this is above 100,000, so we should have a failing required statement with this error message. Then we're going to try to do the airdrop if there is a wrong recipient, so we create a signature for a recipient. Then we create another address, and we try to claim the token of a wrong recipient with the original signature. So the recipient that was used for the signature doesn't match with the wrong recipient, so we should have a failing required statement with this error message wrong signature. Then we're going to try with the wrong amount, so we create a signature, create a wrong amount, we try to claim a token with this wrong amount, and again we should have wrong signature error. And finally, what happened if you try to claim the token with a wrong signature? So here we create a signature, then you create a wrong signature, then we try to claim the token with this wrong signature, and again we should have a failing required statement. So that's it for the smart contract. Next we're going to see the backend. It's possible to use the same project to build both the backend and the frontend by using the Next.js framework. So we're going to use this framework. So in the GitHub repo, we go to Airdrop. That's our Next.js project. So I'm going to pages, and the backend is in API. So we're going to have one endpoint which has the responsibility of creating a signature. So authorization.js. So first of all, we import Mongoose, which is a library to interact with MongoDB. So we're going to use MongoDB to store the list of whitelisted addresses with their allocation. We're also going to need Web3 to produce our signature. So here below, this is some boilerplate code in order to interact with our collection of recipient in MongoDB. And after in Next.js, you can create an endpoint by exporting a function like this. So when the frontend will request a signature, this endpoint will be executed. So first we're going to connect to our database. Then in our database, we're going to fetch the record for the address of the recipient. So that's the frontend that's going to give us this address. And if we find a record in a database, we're going to create a signature. So we use Web3 and we use the 3DT SHA-3 hashing function. So we're going to pass the address and the amount that was stored in the database. So at the end of the registration period, I'm going to run a script that will determine the allocation for each address. So after this line, it's a bit weird. So basically we have to instantiate a new instance of Web3 in order to use the sign method, but we don't need to actually connect to an Ethereum node. So that's why I put an empty string here. And so here is where the critical part happens. So that's where we produce the signature. So we pass the message that we produced just before, and we're going to sign with the private key of our admin. So this is going to be stored in an environment variable on the backend. And after, we are going to return a JSON document with the address, the amount of the allocation, and the signature. And after, that's the end of our endpoint. Otherwise, if we reach this point, it means that we haven't found a record for this address in our database. So this address is not whitelisted. So we answer with a status of 401, which is unauthorized. So there are always a lot of different opinions on what is the best HTTP status to use. When everything goes well, there is no discussion, usually it's 200. But when there is an error, there are several possibilities. So I chose 401, but there is also 403 that has a similar semantic meaning. But let's not waste time too much on the details. So that's it for the backend. Next, we're going to do the front end. Okay, so let's see the code of the front end. So we go in the Airdrop folder, and first I wanted to talk briefly about environment variables. So in Next.js, you can define a file called .env. So here .env example, you need to rename it to .env if you want to make it work. And inside you can define your environment variable, and these will be available in process.env in your JavaScript code. If you want the environment variable to be visible to the front end, you need to prefix it with next public like I did here. So make sure to not put anything really sensitive with next public here, because everybody will be able to see this info. And when you are running your app in production, I don't recommend to use a .env file. Usually the hosting company has a graphical interface to define environment variable. And also make sure to never commit your .env file. So here this is .env example, this is fine. Never commit your .env file where we have actual value in it. Okay, so let's go back to Airdrop, and then we're gonna go to pages and ethereum.js. So that's where we are going to create our connection with the blockchain. So first we import MetaMask detect provider. This is a library to detect MetaMask. Then we import Web3 to interact with the blockchain. Then we import airdrop.json. So this is a file produced by Truffle with the detail of the deployment of your smart contract, including the address. Then we define our function getBlockchain. First, we're going to detect MetaMask here, and we're going to get the provider when this is detected. If we have detected MetaMask, so we're going inside this if block, and first we are going to ask the user to grant us access. So the user will see a pop-up and he will have to accept our application. And after that, we're going to have the list of addresses that are managed by the MetaMask of the user in the accounts array. We're also going to get the current network ID that is configured on MetaMask. And after, with this if, we're going to check that MetaMask is configured on the correct network, and this is based on what we have in next public network ID. So with this, you can have different deployment for your Airdrop app. You can have one for mainnet, but also you can have one for testnet. And if we are on the wrong network, we're going to reject the promise with an error message, and we're going to see after how we can process this error. After, if we continue, that means there was no error, everything is fine. So we instantiate a new instance of Web3 with the provider of MetaMask. And after we create a pointer to our Airdrop smart contract, we give it the ABI of the contract, which is basically a JSON interface that defines the solidity function that we can call. And for this, we use the JSON object Airdrop that we imported from Truffle. We also use this JSON object to get the address of our Airdrop smart contract, and this is indexed by network. Finally, we resolve the promise with the Airdrop object and the accounts from MetaMask, and we stop here. And if we continue, that means that we didn't detect MetaMask, and in this case, we reject the promise with an error message. Okay, so next, we're going in the main file, index.js. That's where we do the heavy lifting. First, we import some stuff necessary for React, then some detail for Next.js, nothing really interesting. Then Axio, so this is a library to do HTTP requests, and we're going to use it in order to interact with our backend. Then Web3 to interact with the blockchain. Then the function getBlockchain from ethereum.js that I just explained before. Then we define our home component. So in our app, we're just going to have one component. Then we define the state of our component. So we're going to have a loading state as long as MetaMask is not loaded. We're also going to show some feedback to the user with a loading message. We're also going to have another state to provide some feedback when the user is claiming the token. And we also have a state for the airdrop JavaScript object that point to our smart contract, and also a state for the list of addresses managed by MetaMask. So after use effect, so this is executed only once when your app loads for the first time. So this thing is going to be executed. So first we call getBlockchain, and we're going to get airdrop and accounts. So we save this in the state of the component, and we set the loading state to false because at this point we have everything. And after, the component is going to re-render because the state has changed. And if any error happen in getBlockchain, for example, if we don't find MetaMask, then we're going to catch the error here in the catch block. And in this case, we're going to display the error thanks to the loading message state. Okay, so after, so we're going to skip this function for now, claim tokens. Here, that's where we return our HTML. So here's some static HTML. After, when we are loading, we're going to display a loading message. And after, when we are not loading anymore, we're going to display the actual content of the app. So first here, this is some instruction to claim your tokens. And after, this is the most important. This is the form that we're going to use to claim our tokens. So there is a single input that's for your Binance Smart Chain address. Then you click on the button to submit the form and trigger the claiming process. And below, you are going to show some feedback to your user with the claim message state. And so when you click on the submit button, it's going to trigger the onSubmit event, which will trigger the claim tokens function that we define above. So we go up. And here in our function, first we call prevent default on the event object. This is going to prevent a full page reload. Then we extract the address of Binance Smart Chain. Oops, I just realized I don't have the latest version of the file. Let me reload this. Yeah, just a tiny detail here. Okay, so this is the correct version. Okay, so here we're going to display to the user some feedback. So now we are checking your address in the whitelist. And after, we are going to create a signature. So you can send HTTP GET request or POST request. But since we are creating a resource, we're creating a signature, semantically I prefer to use a POST request, but this is just a detail. And here we put the URL of our backend, and the path to our endpoint is /API/authorization because we created a file called authorization.js. And in the body of our HTTP post and in the body of our HTTP post request, we're going to pass our address. Then the backend going to check that we are on the whitelist, going to create the signature, and it's going to return all of this in a response. And after that, we're going to update the message to the user. So now we move on to the stage where we send a transaction to the Airdrop smart contract to actually get your token. And after here, so very critical phase, we actually send the transaction to the Airdrop smart contract. We call the claim tokens function with all the argument. So coming from the backend, so the address, the allocation, and very importantly, the signature coming from the backend. And we send this from the first address of the accounts array, which is the address currently selected in MetaMask. And after, the transaction is mined, so the airdrop is a success. And we display the detail of the airdrop to the user. And we wrap everything in a try-catch block because there are different errors that can happen. First of all, it's possible that our address has not been whitelisted. And we can detect this if the error has this string. So in this case, we inform the user that the airdrop has failed because the address was not registered. And if this is not this error, it means that the error came from the smart contract. And so in this case, most likely it failed because you already claimed your token before. So you try to claim your token twice. Okay, so as you can see, the code is slightly more complex than my usual tutorials because this time this is a production application. So I have to deal more carefully with the different corner cases, the different errors that can happen. Okay, so we're gonna stop here, and next I will show you a demo. So for the demo, I'm going to the terminal. I'm in my project. So first, at the root of the project, I've already run npm install to install all the dependency, and then I run truffle develop. So I'm going to do the demo on a local development blockchain. And after this video, I'm going to do a deployment on a public testnet. And with a few students of EatTheBlocks, we're going to test the app on testnet to make sure that everything works fine. And after that, I will deploy the Airdrop smart contract on mainnet. But now the demo is just on a local blockchain. So first I deploy the smart contract, the token, and the airdrop. And in my migration file of Truffle, I also send 100,000 token to the airdrop smart contract. Okay, then in another terminal, I'm going to airdrop. Then I've already run npm install, and after to run the front end, I run npm run dev. That's the command for Next.js. Okay, this is available at localhost 3000. And then I go to my browser and I load this address, and then I go to MetaMask. So this is connected to my local development blockchain, and I'm going to reset the account. You need to do this every time you reset your local development blockchain. So we go to settings, general, oh no, it's not here, it's advanced, reset account, reset, yes. Okay, then I'm going to configure the tokens. Okay, so I'm going to remove this one. I did a test before. So I click on add token at the bottom of the screen, custom tokens. Then I go back to the terminal. Then I go up in my screen and I copy the address of the EatTheBlocks token. Then I go to MetaMask, add token, custom token. Okay, so then I click on next. It's cut off on my screen. And so I have 900,000 EatTheBlocks token because I'm the admin of the token. But after I do the airdrop, I'm going to have one more token here. So here I click on add token. And I've also created a MongoDB database, and I've added manually a record for my address. And for the amount, I think I put one EatTheBlocks token. We'll verify this. Then we copy our address to the clipboard. So this is the front end of the app. We paste our address here. We click on submit. So we see the feedback message here, and we see the confirmation pop-up of MetaMask. So we confirm, and the airdrop is a success. We can see the transaction hash here. So we were sent one EatTheBlocks token to this address. And so after, let's check our address here. So we can see that we have 900,000 one EatTheBlocks token. So the airdrop was successful. Did we achieve our goal of building a decentralized airdrop system with a low gas consumption? For the low gas consumption, from my point of view, the creator of the airdrop, I will only have to deploy the contract of the airdrop, so that's okay. And from the point of view of users, it's fine too, since they only have one transaction to send to claim their tokens. When it comes to decentralization, it's not great because there is a centralized backend that produces the signatures required by the airdrop smart contract. If the backend is compromised, it's possible to censor some addresses, but this was a compromise required to lower the gas spending. If you haven't done so yet, make sure to register for the airdrop of the EatTheBlocks token. You have until April 30th to register, and I put the link down below. You will need a Binance Smart Chain address where you control the private keys. This includes addresses managed by MetaMask, software wallets, and hardware wallets. This does not include addresses managed by centralized exchanges. Not all wallets allow to create Binance Smart Chain addresses, but that's okay because any Ethereum address can also be used for Binance Smart Chain. So go register for the airdrop to make sure you will receive some EatTheBlocks tokens for free, and after with these tokens you will be able to vote for the content of EatTheBlocks on YouTube. And later there will be other capabilities that will be added. I will see you in another video.